design in a kitchen for the small outlet. Are we together?
Yes.
So we come to other rooms. So like in the sitting room, of course you expect in the sitting room at the TV unit position to have at least two of these two gang socket outlets. Why? Because that's where you expect a lot of appliances, electrical appliances there. You expect speakers, woofers, you expect this TV itself, you expect a decoder. So it is really good to do what? To have these you have these two with a satellite television unit here, outlet, because you expect a decoder here, or maybe this outlet satellite straight to the TV for these free what? They are called what? Free where you don't pay subscription, so you
Free
will
to
have
air.
to get free to air. Yeah. So of course you put, as I told you, this socket positioning are judgmental, but of course you also have to picture out the convenience to the what, and also maybe your client, what he says, what is his opinion on maybe those sockets, because he might not be well convenient. The pricing maybe he tells you, please reduce those number of sockets, but it doesn't hurt having key socket, and that also maybe this position here for these guys seated here, maybe they are charging, maybe you're charging you seated here, you want to charge a phone. Yeah, it would be convenient for you. Maybe you're using a laptop at this position when you're seated here, so you might have it here or this side. You can have a socket here or here, but I don't expect you to put here then here. So you can have it here. You can also have one here. So as I've told you, it is really to the customer's desires, and so you can design your initial, but remember you will have to adjust based on the customer, what the customer says, what the architect says. These architects are more good into these things. They can tell you, really, that those sockets are too many for my customer. Maybe remove this, maybe do this. So you be ready to adjust accordingly. So you come to this guest house, bedroom maybe. We have these two sockets side and side. It's a good design to have them here and here. Assuming this is to accommodate two people. One would be sleeping on this side and using this here, and one sleeping this side using this here. You can put one here, one here, or this. It's actually more preferable to have a socket at the door at this point, than here. Are we together, Martin? So it will
Yes.
be more appropriate to have close to this door outlet here. Why, for what purpose? Maybe they can mount here a television or a radio station here, sorry, not a radio station, but a radio point at that position. Speaker there, so you can put here also what, an outlet. It is more preferable to have it close to this door at this position here than having it this side. So you come here to the bathroom. Not every bathroom will have the shaver socket, but this one for the guest room, of course, for a fancy home, you can put this in the bathroom for the guest room, bedroom. You can put your shaver outlet here, but not in this common washroom. This toilet. You can't put here a shaver socket. Will someone come and shave from here? Of course, it's not applicable. So you put that. Yeah. So literally, that's how you could position your what? Your socket outlets. Here we didn't put here because you can see this is an entrance to this point. Maybe you would have put one here. Are you seeing Martin there? You would have put one here, someone seated here. You put that one for any person seated here. Also this one here, Yeah, you can also put, but you can see really you don't expect much to be used here. Find an architect might maybe tell you also here there might be a TV unit here, So you have to just be really flexible. You send the first draft of your drawing to the architect. The architect may tell you, I already add some sockets here or remove this one, So we have our consumer unit. Really, for the principle of positioning the consumer unit, it is really factors that you would consider for its position. You would, first of it, you consider the distribution of the load. So it is really preferable to have a consumer unit that is, yes, Martin, any question?
No, no.
I hope you know what a consumer unit is. It
Yes,
is, you know it, eh?
yes. The main distribution point.
It's not a
From
main. If you term it as a main, in any building there is a one which is main and also those that are sub, I would say sub, but it is just a distribution point in a house. So a consumer unit is typically a single phase. It is really typically for single phase. When you come to three phase, it is termed as a distribution board. Are we together? For single phase, it is a consumer unit. For three phase, it is termed as a what? A distribution board. Yeah, a distribution board. So assuming this home was really a huge one, and in calculation of your load, you'd come to maybe a current of about maximum load of about 120 amps. So that for such a consumption, you would really require to, most standard British breakers for single phase really end up to 100 amps preferably, but I see on market they also produce those of 125, 120, but I don't expect much exceeding 120. 120. So it preferable if you calculate your load up to maybe exceeding 120, you go to three phase. Are we together? And for three phase distribution, this is now changing from a consumer unit to a distribution unit. We together?
yes,
Yes. So I was telling you factors to consider for your positioning of your consumer unit or distribution unit. One is really it should be centralized in a way that the distribution to the different points, you see, it is almost in the center, whereby you would run a cable from here to this room. It is really easy. Also from here to this kitchen, it is really easy. From here to the dining room, you see the accessibility. It is really centered there. That is one factor. The other factor you could consider is its distribution from the main. You getting me? It's distribution from the main. So you might find, if we had a site plan here, you'd find maybe you assume the gate or the gate is this side, far away from this position. Really, you can't. It's not preferable to put your consumer unit here, because really this is the entrance. It is really more accessible. It's also good to put your consumer unit in points where it is not accessible to kids. Such factors that you can supply fairly tuning of your load. So really that is the distribution that we did here. I mean the small power outlet here. So when we come to the next flow, I want to go much into the fly, like you're not deleting off these grids, because you find, when you to analyze this grid positioning, you can see for the lower ground, this is actually called low ground floor. While detailing details of this building, you really identify that there is a lower ground. What do I mean by lower ground? It means that have you ever come across these homes like it is being built on kind of a hill, whereby you'd find one floor of the room of the building having a lower ground, like in other words, it has a ground, though it is down. Yeah? Then you find the next floor also having a ground. Like, let me give an example. Have you ever been to Frama Hostel, Martin?
Farmer?
Frama Hostel.
Farmer hostel. Is it in Chikoni?
Yes, in Chikoni.
Yes, in Japan.
Which other hostels around it? I try to remember.
It is close to. It is the only hostel as you're heading to this side, sloping to that side of Wise, going to Wise, that road. You see, you leave Can. Now, as you stay on Main, as if you're going to Wise, now that hostel there. I don't know whether you've ever been into it, because it would give a clear picture of what I'm describing. Let me say building. Okay, let us say that. You see, say that old building, Yeah, old building. Assuming that entrance to the old building, that main entrance, that side,
Yeah.
it is like a bridge-like thing. But you assume there was there was a ground up to that level. Don't assume that it is a bridge, but assuming there is a ground up to that level. Then you go down the other side behind it. So you can see that building, it would have two grounds. In other words, there is a lower ground that would be down behind that building, behind, which is lower than the ground at that level. But you
The
see,
front.
at this front, then also at its behind, you would see there are two. There is a lower. You've got my point.
Yes.
You would see there is a lower ground and upper ground. Yeah. So this is the building that we are having really here. So you would see. Sorry, we are here. You would see for this position here. This is a lower ground at this end. I mean this side, this front. Its front is lower ground. So at its back, sorry for that. At its back here, you see there is even no window-like thing, because this ground runs up to up. So this is called a retaining wall. You see, this wall is called a retaining wall. Why? Because the ground at its side, outer side, it's just a ground, running up to up. So that's why you see even in its lighting, we didn't put any light behind it, because this is ground. You're getting my point, You're understanding this layout,
Yes.
So when we really trying to, I brought up that because we are trying to understand these grids, how they are running. You can see this grid is running from 1 to 5 on lower ground. So you come to upper ground, it is really running from 1 to 7. Do you know why? Because up to 5 here, to 5, this is the other side of lower ground. If you to stand here and view this building, at lower ground, you would see this is like at lower ground side, you would see that now the Kalina in it. But when you come to the back here, This is a ground. At the back, the way I've explained it to you, when you try to picture it from the cedar tall building, the way I've told you, the side you would say ground, so you can even see why we have a pouch here. This porch, meaning there is an entrance. You can enter from here or you can move out. You see we're having even rooms this side, yet it is on the upper level. So this is called upper ground. Then the other one is a what? A lower ground. So if you to picture it with the way I've explained to say that, in terms of say that, this would be the, let me say, the agriculture, the other, I don't know, that college, that other college, close to Sedat, or the parking in Sedat, that parking at Sedat old building. This would be that parking. So this side here, you would be maybe in some classroom that is above the ground. You getting me? I hope you've understood that topology. I don't know. But anyway, we continue. So my purpose of bringing that was, by the way, a way of learning how to interpret drawings. Yeah, to be cautious of background and lower ground. So you can maybe research more about that. But back to the electrical, I was explaining the grids. So you can see we had positioned our CU here on lower ground. At that position. So you can copy it here, because you're going to raise, there's a CU above, exactly above it, so that the cable just runs straight up to supply the flow, the other flow up. So you can copy it like that. You come to maybe 5 and A, you copy, you select it from there. We're copying selection, are you seeing? So moving it to the same position above, on the next floor above, I'll have to look for 5 and A, around there. So I position it there. You see? So that has given us a reference based on the grid. So when you come to see here, you see it has really come to that position. Though I'll put it in the lighting layout. I had to put it in the what? Socket layout. So when you come to the socket layout, that's why we positioned it there. Have you seen the use of grids, Martin?
Yeah.
Yeah, that's what I was trying to explain to you, the exact position above. Why are we positioning it there? Because this is like our main CU, our main consumer unit on lower ground. So it is from this that is going to distribute up. You getting me? So distributing to this upper flow. So really the positioning of sockets, I've told you, it is really judgmental. You can see this is like our master bedroom. This is like someone can sit here to read. You expect to have a socket there. Someone can sit here to read, someone can be on PC, someone, the way the arrangement, you can see it. So it is really judgmental. You can decide to put there a socket, same as here, same as here. Really, you can see the necessity of having a socket there. So you've come up with your positioning of sockets. Now we come to the circuiting. As I told you, this session is going to be rapid, so we come to the circuiting. So circuiting really requires you to know the background of cable sizing, load calculation. This is where our electrical engineering is. Are we together? Who? Martin.
Yeah, load calculation. You have to calculate the loads, then find the size of the cable that can supply those loads.
That can sustain the load. It is from load that you select the circuit breaker. We select the circuit breaker that is really bigger than the what? A little, the higher, at a higher capacity than your calculated load. Then it's from there that we select the what? the cable size from the our British standard, BS, from BS 7671. Are we together?
Yeah.
Yeah, you have to familiarize yourself with those tables. Really, I'm not going to drill much into that because our scope of work here is AutoCAD and coming up with those layouts. So for that electrical background, I know you did it with, I don't know, either Dr. Bakabalinde or some lady, I'm forgetting her name, if you're from Makerere. I don't know where. If
Yeah, I'm
not,
from Muk, but yeah.
yeah, that's why I was talking about Dr. Bakabalinde or some lady. I'm
Yeah.
sure you did electrical installation design
Yeah.
and you try to learn about BS. So another task for this week, I want
Yes.
you to familiarize yourself with you try to revise how to do load calculation. There are literally two methods for load calculation. One, there is the standard one. You have to know the load based on the design they have given you. Now, for example, let me go through only that. Really that. Let us go to ground floor here. Here there you expect to have a television. You expect to have a woofer, also a sound system. You expect to have what else? Decoder. So, in other words, that method is knowing the load by having the consumption for each appliance, each and every appliance and equipment within your home. Yeah? So that is one way of knowing the load. So you get all that load. That is the most method, though it is time consuming. And also this really is over experience with time. You can really just know, okay, based on this is our load. Then the other issue is for load calculation. There is I would recommend a book called Wiring. I don't know, electrical. It's called Electrical Wiring. Forgetting it. It's called It's called Guide to Wiring Installation. Electrical installation. Guide to electrical installation. Wiring installation. You can see. You can. Let me try to look for it here. As you see, it can help you in your research as I told you initially that for electrical design, for any engineering design, research is part of you. So let me search for it here. It's guide to wiring installation. It has BS 7. It's not the exact BS, but it has some notes. It has those things that I'm trying to I don't know whether I'll come across it here. This one. This is wiring regulations, no? The other one is wiring Let me first see this one. It's not this one. Maybe let me move this BS. Forgetting that textbook. I've taken long without using it because of, as I told you, with time and experience, you get to know these things at head. It's not this one. It's not loading. Anyway, let us not waste time. It's not this one. It's not this one. I'll be sharing it with Bill. I have it on my drive, my Google Drive. So I'll be sharing it. But however, back to what we were doing, it will help you. It will be a good revision. But also YouTube is also a good resource. But as I told you, it is good to work with textbooks. So back to this. So you can see this wiring schematic here. So I told you we're going to learn how to do what? Circuits too. You've put your sockets, you've put your lighting. Now you really have to put them into circuits, different circuits. You having this, these are different electrical circuits. Like you creating different circuits. I hope you know what a circuit is. A connection of equipment. You categorizing them into different circuits. So that's why you see here lights, GC1. What do I mean by GC? Ground floor, circuit 1. To light circuits. Light circuits, ground floor, circuit 1. And based on the, if you go back to that ground floor, first of all, you're going to first categorize these lights you've done. You try to put them into the what? Into the circuits, as I've said. So we start with ground floor. Really, we are having this circuit 1. So why my choice of circuiting like that? So I'm trying to make sure that the number of lights in that circuit are really, first of all, they are really isolated well in a way that you try to put them, let me say, I would categorize the dining area maybe with the sitting area first, with also security lights being, I mean the external lights, not security lights, the external lights being put into one circuit. You would maybe try to take up that position, but also, putting different wiring main wires, the main wires from the consumer unit into the same, this is a 5 gang, if I'm to calculate 1 2 3 4 5 5, if I'm to count 5 gang socket. Are you seeing 5 gang two-way circuit? So you putting 2 circuits or 2 cables from the consumer unit into this one, it is really difficult. You're getting me? It is really difficult. You might even cause short circuits between those circuits, those designated circuits. So why did we make the you see GC2, this circuit have all these up to this side? It's because of, after us designing, these these switchings are really done before. You really do them before what? Before you circuiting. You're getting my point, Martin? So why do we really have to put all these lights into that single circuit? It's because of these sockets that these switches that we really designed initially, because we made a 5 gang socket here, a 5 gang socket here. So we expect having the same circuit within these interconnected lights. These lights connected to the same same socket. I mean same switch. Sorry, it is the same switch. Are we together? So you would see that switch here is accommodating these lights here. It's accommodating these lights here. It's accommodating these lights here. You see, accommodating these here. So that interconnection also forced us to have these lights being in the same You can see our circuit running from this position, this side, coming here, also taking up these others. These are not really in the same socket, but we're trying to make sure that we have like an area, like, let me say this, all this side being into you're seeing all this area. Let me highlight it. Having this area here like this being into the same circuit. Are you seeing such a thing? Then these ones also come into play because they are already connected to to those sockets. I mean, to those switches. We together, Martin? Martin?
Yes, please.
Are we together?
Yes.
Yeah. So those are some of the really the criteria you'd follow to put the equipments in the same circuit. So, but after me choosing them to be in the same circuit, are really these lights going to be accommodated by that circuit? That is another question that comes to your head. So you can maybe count these lights, these spotlights. You can maybe count them, and based on the research you've done and maybe the specification of these spotlights you've chosen, you can get their wattages. You consider their wattages. So maybe these lights are, if I'm to count these, like those are 3 already, those are 6. Those are already about 11, then about 15 there. You count, so about this circuit might have about 30 lights. So you can get those 30, maybe your wattage per each spotlight is about 10 watts, based on your data, your product data that you've got, your data sheet you've got for that product, for that maybe each is 10 watts. So 30 times 10 watts, that's 3 watts, that 1 point, about 1 point what? About, let me say 1.1. 1.2, yeah? Are we together? About 1.2 amps, 102 there. Are we together, Martin? With this calculation, because it is really, 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 really important. I remember doing this a bit in the lighting design before, explaining to you in-house. The other time we were looking at a parking, in that design. So here, I'm assuming we're having, like, let me say 30. Spotlight. So each is about 10. So 30 times that's about 1 point something amps. Considering the fact of inrush currents, which I remember telling you to read about it, based on that product, they specify all those things on the data sheets. Yeah, so assuming an inrush current of about 10 times the current, which will give you like about 10 amps. You getting me? Are we together on that point? So 10 amps. So you've really identified, yes, that is 10 amps of that load for that circuit. So when we come back to our circuit, the one we designed, you see, we really put what? The 10 amps for the circuit breaker. Then for the 10 amps, and also considering all that distance, you go now to that table for cables. Are we together? Martin? Martin? Yeah. So we go to the table. Does really 10 amps accommodate that with all that distance? Now, for me, I do have this that I confirmed. I do have this app. Let me show it to you. This website, not app. I confirmed it. It is one that really helps me, but I confirmed it with calculations. It helps me out to do cable selections. So it is here. It's called Eland Cable Calculator. Are we together, Martin? So you come to that website. You can maybe use this website to ease your work. So you specify which standard you're using. The conductor, of course, for British standard, for insulation, it is really copper. Which phase are we dealing with? Single phase. Which installation method? Of course, we are conduit. There are cables in conduits for lighting. Are we together? You really have to know all that background, which I'm not dwelling into, because I hope you all have that electrical background. So it is in conducts. Where is it? Enclosed in conduits, sorry. Conduits configuration, single cables touching maybe. So which load have we calculated? We've seen a load of 10, assuming maybe all those lights are switched on at the same time, but which is really difficult to happen, because that inrush current will happen when you switch on all those lights at the same time, and you're seeing those lights, as I've shown you to them, that they are having different different switches that are really switching them on. So maybe you would find, let me say, a maximum of 10 spotlights being switched on at the same time, maybe in the sitting room, where we see, let me show you, maybe here in the sitting room where we see most of the spotlights there, where we can switch them on at the same time. You see, maybe here, and also this decorative light. So you can maybe switch them on at the same time, so that inrush current may be about 5 amps. So we can consider our length of, you can see, you can come to your drawing, try to really span the length, from your CU, which is about here. So you try to measure, really measure those distances, from point to point. Okay, my PC is flowing. You try to measure from this point here, midway, to the extreme ends of the house. Let me say that point. You see, those about 8 meters. So you can consider 10. Or you multiply that times 2, because you're going to run that cable that side, then you have to move down into the walls, to the socket, so you can multiply that by 4, let me say, or by 3. So if we consider, let me say 30, or 35 meters. So if I calculate, what cable size am I getting? So you see, it can still handle. Have you seen? Martin, are we together? So this is one of the tools that can really, really support you. Even if I increase my length to, let me say, about 50. No, now there it has run. But I'm sure it can't exceed, because we've seen from remember, you are laying into the ceiling, ceiling void. You are laying those cables in the ceiling void. So if you run a cable from about 8 meters, so those droppings that you can really account for, they can't really reach, if already that is 8, so they can't really exceed 40. That is too much of it. 40, 30. So it can really handle, because this 10 I've calculated for the whole lights, yet I'm calculating the length to some certain corner of the house. So it is really too much. So really 30 is enough. So the 1.5 millimeters can really accommodate that. So we together. So you come back to your design. So I've really justified this, why we're selecting the 10 and the 3 times. Now this this cable type, why am I selecting 3? As I've showed you here in the selecting of the cable, I said single core attaching. Of course, if you go back to the wiring thing, those are things that we did in recess, Martin? That knowledge you did in recess, you would see when we are doing the lighting installation, you saw we used single core cables. You would see the red, I don't remember, red, yellow, and what? Maybe green and a red, black, and the green. For red for the live, black neutral, then the green and yellow for the earthing. So it is what I'm specifying here, which is the 3, meaning 3 of them, each having 1.5 millimeters copper cables in conduit. You're getting my language there. So we can get all that load, the lighting load, like that. Sockets are usually supplied by 32 amps usually, but also you can, based on the load you've calculated, you can even reach 40 amps Then the cable sizing, it's also based on the appliance. They will have the same thing I've done for lighting. You can let us say a case for one case for the small power. If we come to the ground floor, we have two circuits. We have about 3 circuits here. So we're seeing the G3. Why? We are seeing G3 being supplying all over up to this side, because really the appliances put here, you're going to just put a charger which is about at most 30 watts. At most, that is even too big. At most 30 watts. You're getting me? So you're going to put a charger, a TV. So really you have to go and read about the wattages of these electrical appliances being used. So it is very good and very appropriate to separate the circuit that is supplying the kitchen appliances from the rest, because these ones are really heavy and they have different characteristics, this different behavior from the appliances being used in this side. You getting me? So really the kitchen, you can see the kitchen circuit is separate from this. That's why here we selected the circuit 3 supplying everything the rest of this floor, because it is really small. It is really small. And also comparing each socket, you can see here, what do you expect here really? It's something small. So you can assume maybe here there is a charger, or maybe there is a woofer here there is a charger, here there is, they are charging from here. You estimate all those what? Because this is estimated load. You estimate every appliance you would expect at the point where you've put your socket, you sum up that, you get that load. Are we together? So you come to the kitchen. It is a must. Give these appliances a different these sockets here. Give them a different what? A different circuit here. So you can add also this water heater to this, based on the size of also your kitchen. You can add this water heater separate. You can give it a separate what? A separate circuit. You can give it a separate circuit. Then it is a must to have a cooker having its own separate what? Circuit. I think you're taking note of these things, Martin. Hopefully you're taking note of this, because these are must things on your fingerprint that you have to consider. Cooker control unit, because really heating elements consume a lot of power compared to anything here. This cooker unit, its own what? Its own. So come to our wiring schematics here. Ground floor. So we are seeing, I've showed you how you would segment these lighting circuits here. And then I have showed you the sockets here for the small power outlet. You can see in the kitchen we gave it its own. We added just a spark to the kitchen water heater. I hope you know what a spark is. It's like having your circuit breaker here, then you attach 2 cables from it. You attach the main and another cable. So in other words, you're having 2 cables running from the what? From the same circuit breaker. So that is a spar to the kitchen water heater of the same size, 2.5. So we come to the cooker. This cooker and extraction wood. I hope you all know that. We are giving it a 4, because this cooker, as I told you, the load, the electrical, the heating elements, you can even go and search about wattages, the load of these cookers. So you would really know why we're having that 4 there and the 32. So now we expected some HVAC power supply. We really don't know where they are going to supply, but we expect an HVAC which we give a 6 and a 32 amps. But as far as it goes on, really what we interested in is the main, because this main supply to the house, it gives us the capacity. In other words, if our customer, the client really expects to have more HVAC units, does this capacity, this overall capacity outside, can it handle that extra HVAC units? Then we have this supply to the what? To the first floor, as I told you why we did the other vertical layout. So we supply this to the upper floor. So as I told you, this is based on the load that you're going to calculate from the what? From the first floor consumption. Then you specify this breaker and the cable size. Then we have a DSQ. I think you know what a DSQ is. It is called it's called a servant quarter. It's called servant quarters. I'm forgetting the D, what the D stands for, but literally it is this. Why did we give it a 10? Because you see we are also having a cooker this side. That cooker takes a lot of consumption. As I've told you, go back and read about typical wattages of those what appliances. Really, they will give you a clear picture and understanding of these selections. And we gave it an insulated cable, a 3-core. In other words, we're having the 3 cores, all the 3 cores being insulated into one cable. Why did we select that? It's an insulated cable because we are moving from one building to an outside building. You can see it is insulated in that way because you see we are going to move literally from the ground floor this side, from this CU on lower ground. We have to move it up to this point here. You seeing, to this point. So really we have to work with an insulated cable. Are we together, Martin? So that's why we selected it to be insulated. Yeah, we have to be cautious of that. Then for upper floor, it is really, I mean for the upper ground floor, it is really flexible cable from the CU. It has to just be flexible to pass through the what? To pass through the wall. Yeah? We pass the flexible cable through the wall to the next floor. So those are the selection of our cables.
Akram. Hello. Martin.
Yes, please.
Are you guys okay? Is everything flowing well?
Yes.
Yeah, okay, fine. I'm also here.
Okay.
Hello? Yes. I told you, sorry for that interruption, but literally that is the cable sizing and the